Okay, so last time we talked about the three elements of a probability space. So we can briefly review them. So for any random experiment, we first have an omega set, okay, which is the set of all outcomes. And then we call every subset of omega an event. So that's the definition of the event. And on top of that, so we collect some events to form a sigma algebra or sigma field. So that field is denoted as capital F. So this is the collection, the sigma algebra of events. And for the sigma algebra, we talk about that it must satisfy certain conditions. And then once we have this sigma algebra, we can define a probability law on this sigma algebra. So that is called P. So for the P is a function that maps every event in this sigma algebra to a real number between 0 and 1. Okay. So that's how we assign probabilities. In the modern probability framework, we assign probabilities to the events in this sigma algebra. And last time we talked about the conditions, the requirements for this probability law. So it must satisfy several conditions. The first condition is that the probability must be between 0 and 1 for every event in this sigma field. And second one says that the probability of this event, this omega event, okay, omega is an event because it is a subset of itself. So this event contains all the possible outcomes. The probability of this biggest event is 1. And the last one says that if we have a bunch of events that belongs to this sigma field and they are mutually exclusive. So we have a bunch of mutually exclusive events from the sigma field. And then because they are mutually exclusive, intuitively, we would like the probability of their union event. So the probability of the union of all these events equals to the sum of the probability of each individual event, because they are mutually exclusive. So these are the three requirements for the probability law. And then we have a comment that we call an event. If an event has probability 0, then we call it a null event. And if a probability of event A equals to 1, we call it an almost sure event. Okay. And we have an example last time to illustrate why we call it almost sure. Okay. So the example is that we consider the event sample point uniformly from this interval, and we consider the event A. Well, let's call this sample point omega, call it omega. And let's consider this event A. Well, this omega is not equal to 1/2. Okay. And this is an event because the omega set, the set of all outcomes is simply 0 and 1, this entire interval, right? Because you are picking a point uniformly from this interval. So all the possible outcomes simply forms this interval. And then this event A corresponds to I should say I should take an intersection with this interval. So this A, event A, corresponds to the case where the sampled point is everything within this interval except for the middle point, 1/2. Right? And this is a subset. This is a subset of omega. Right? It is simply this interval excluding the middle point. Now this is a subset of omega. Therefore, this A can be called as an event. Right? And according to the probability law, we know that P omega is 1. We know that P omega equals to 1 by the probability law. And moreover, we know that the probability that you sample the middle point is 0 because we have infinitely many points in this interval, and we pick every point uniformly at random. Okay, therefore, the probability that we pick this point is 0. Now, this event and this A event, they are mutually exclusive, right? This event means we pick the middle point, and A event means that we pick every other point except for the middle point. So these two events, they are mutually exclusive. Therefore, by the mutually exclusive property of the probability law, we can conclude that, and their union, if you union these two events, they simply become the entire interval. Okay. So P A union this event. Now these two are mutually exclusive. Therefore, by the probability law, we know that it equals to the sum of the probability of these two individual events. And on the other hand, if you look at this union, A union 1/2 is exactly the interval 0 and 1. So this is actually omega. This is exactly P omega, which equals to 1. Okay. Therefore, you can conclude that 1 equals to PA plus P1/2. Well, P1/2 is 0. So you conclude that PA is 1. Okay. So the probability that this event happens is 1. And this is where you can see why we call it almost sure event, because this event does not include all the possible outcomes, right? It excludes the middle point, but it happens with probability 1. So that's why we put an almost sure in there. Yeah. Yeah. Yes. So because A, if you look at event A and this event, this is also event, right? If you look at these two events, they are mutually exclusive, right? A excludes the middle point, but this event is exactly the middle point. So these two are mutually exclusive. And for mutually exclusive events, by the third property of the probability law, right? For mutually exclusive events, the probability of their union equals to the sum of their individual probabilities. So we are applying this particular rule here. So these two are mutually exclusive. So the probability of the union event equals to sum of these two events. And then you realize that the union of these two events is exactly omega, because one A excludes the middle point. Well, this is exactly the middle point. Once you put them together, you actually get the entire interval, right? So this is exactly P omega, which equals to 1 by default. So you can see that this A event happens with probability 1. But it does not include this possible outcome. So that's why we call it almost sure. Yeah, and there is I want to make a remark here, which is a extension of this result. So here we are picking 1 point from the interval, right? We are considering this. We are basically considering the middle point. But we can consider more complicated events. Again, we consider the same experiments. We sample a point uniformly from 0 and 1. So let me remove this. Consider the same experiment, but let's consider this event B, where the point that you pick is a rational number. Okay. Because we know the real line contains rational numbers and irrational numbers. And this complement event is the point that you pick within this interval is a irrational number. So this Q stands for rational numbers. Q complement means irrational numbers. Right. So basically, when you randomly pick a point within this interval, you may get either a rational number or an irrational number. So the question is, what is the probability? What are the probabilities of these two events? How likely you will pick a rational number and how likely you will pick an irrational number? So this question is actually very challenging in mathematics. But it's a very interesting question because intuitively, we have within this interval, we have infinitely many rational numbers, and we also have infinitely many irrational numbers. Right? Because between every two rational numbers, you can always have an irrational number. And between every two irrational numbers, you can always find a rational number. So it turns out that the probability of B is 0, while the probability of B complement is 1. So you almost surely you will always get a irrational number. So this indicates that on the real line, the irrational number are much denser than the rational number. So this is a very interesting fundamental structure of the real line. Okay, so let's consider two examples on the probability law. we consider the random experiment where we repeatedly flip a fail coin. Until we observe the first head. Okay. So there are two keywords here. One is that this is a fail coin. So we are equally likely we can get head and tail. And the second thing is that we will repeatedly flip this coin until we observe the head. So we have the, for this random experiment, we have the set of all outcomes. We have discussed this before. So we can denote the first possible outcome is when we observe the first head in the first trial. So we flip the coin and directly observe a head. And the second possible outcome is that we are unlucky in the first trial, and in the second trial, we get lucky, we observe the head. Okay. And we keep going on, so we can find infinitely many such outcomes. Well, the ith outcome is simply we observed all tails in the previous I-1 trials, and then in the last trial, we observed the head. Right? These are all the possible outcomes where we flip the coin repeatedly until we observe the first head. So the omega space is simply the collection of all these omega i's. So that's all the possible outcomes. And then we can consider, so the sigma field on this event, we can consider the power set, the biggest sigma field. And then for each particular event, we can, because it is a fail coin, so we can actually calculate all the probabilities maps corresponding to each event. So for example, by default, we have P omega equals to 1, and the empty event is 0. Yes. Okay, so this is this is a notation. This actually means that the set of all the subsets of omega is the biggest sigma field that we can have. Yeah, so it's just a notation. Yeah. This omega in the superscript means that this set has cardinality 2 to the power of omega. So this is just a notation, it's power set. So these two are by default. And then we can consider the probability of every single outcome. Omega I, this omega I, you can think it is actually an event, right? Because it is a subset of omega, of this big omega set. So this is actually an event, but this event only contains this single outcome. Now the question is, with a fail coin, what is the probability that omega I happens? Any idea? So we are flipping a fail coin, and omega I corresponds to the case that, well, in the first I-1 trials, you always get tail, and in the last trial, you get a head. Now, assuming that every coin flip is independent from each other, so how would you calculate this probability? So for every single coin flip, right, you have 1/2 probability to get an H and 1/2 get a tail. Yes. 1/2 to the, okay, so you said 1/2 to the power of I-1, right? So what is the justification for that? Yeah, right. So I think what you just said covers the first I-1 trial, but what about the last one? In the last trial, you still have 1/2 probability to get tail, right? So you need to add another 1/2. Yeah, to the I. So because this is a fair coin, so the probability that you get tail and head are both 1/2. So to calculate this probability, you just count for every single trial. In the first trial, you have 1/2 probability to get tail, and so you have one. So you write 1/2 here, and in the second trial, you are also looking for a tail, and the probability is 1/2. And you realize no matter what you write here, because it's a fair coin, so they always happen with probability 1/2. So in total, we are performing in total I trials. So in total, you are multiplying 1/2 by I times. So in the end, you get 1/2 to the power of I. So that is the probability of omega I. And you can actually verify that if you summing up, you can actually verify P omega is equal to 1. Because in this case, P omega is simply the union of omega I, where I equals to 1 to infinity. We go back, omega contains all the possible outcomes. And all the possible outcomes, they are mutually exclusive events. Therefore, omega is simply the union of all the possible outcomes. And because they are mutually exclusive, so we can apply the probability law to decompose it to the sum of the probability of individual events, individual outcomes. And then we just calculated that P omega I is 1/2 to the power of I. And then you get this summation over this geometric series. So we have a formula for calculating this. And if you apply that formula, you get exactly 1. Okay, the limit is 1. Yes. Okay. This one, right? Yeah. So if we have a to the power of I, summation over a to the power of I. So this would equal to the first one, which is a, right? We start from a, and 1 minus a infinity. So if a less than 1, yeah, if A is less than 1, then this term will goes to 0. So all you have is A divided by 1 minus A. So in this case, A is 1/2. So you have 1/2 divided by 1 minus 1/2, which is 1/2. So you get 1 in the end. And this is consistent because we do have P omega equals to 1 by default. So the second example is a continuous example that we have discussed before. It's a bus arrival between, for example, 0 and 1, let's say. And then the way we assign the probabilities is very simple. It's simply calculating the length of the time intervals that we are interested in. So for any two time indexes between 0 and 1, the probability that the bus arrival is between x1 and x2 is simply the length of this interval. This is very intuitive. Because the entire length, entire time interval is 1. So you have we are considering the bus arrival between x1 and x2. So this interval occupies x2 minus x1 percentage of the entire interval. So this is the probability for the bus arrival. Okay. So this is a continuous example. Any questions? Yes. If you are, let's say, if you're considering between 0 and 2, then it should be this length. Well, it should be the length divided by the length of the time interval. Yeah. So it's the ratio, this ratio. Okay. So up to here, these are all the definitions and the basic properties we have for the 3 elements of the probability, modern probability space. We have omega, big omega, set of all outcomes. We have this sigma algebra of events, and then we can start it to define a probability law on this sigma algebra. Okay, and they all have different particular structures. And I think these structures, if you look at each item, they are very intuitive. And actually, so this is the modern probability framework, but it does cover it has a close connection to the traditional probability framework. They are not contradictory to each other. But this one actually covers the classic one. So let's consider some special cases of probability law. So very special case. So we know that we developed this modern probability framework in order to handle those continuous cases where the outcome space is uncountably infinite. So, but in a special case where the omega is finite or countably infinite. Okay. So if the outcome is either finite or countably infinite, then this modern probability framework actually reduces to the classic one. So if this is finite or countably infinite, then the probability law, which maps the events on the sigma field to 0 and 1, can be defined in terms of the classic way. In the classic way, we assign probabilities to every outcome in omega, okay, to 0 and 1. So this is the difference. So here in the modern part, we assign probabilities to the events, but in the classic way, we assign probabilities to each outcome. So if the omega is finite or countably infinite, then we can simply take the classic way to address the problem. So in particular, how do we define this? So let's say if we have an event, and because the event is an outcome, is a subset of the omega space, so this event may contain a bunch of outcomes. Right. So this event is a subset of the big omega space. So it must contain a bunch of outcomes. Okay. Now, how do we assign the probability to this event? We can simply define probability of this event to be the sum of the probabilities of each outcome. So this is a bridge between, in this case, okay, in this particular case, when omega is finite or countably infinite, this equation is a bridge between modern and the classic probability theory. Because on the left-hand side, we're looking at the probability of events, which is the modern probability theory. On the right-hand side, we're looking at the probability of every single outcome, which comes from the classic probability theory. So they have this relation. So the probability of an event is simply summing up all the probability mass of every single outcome. And this only, you can see that this only holds for finite, either finite or countably infinite, because only in these two cases, you can do this summation. Okay. If it is finite, then this is just a finite summation, or summation over finite events, outcomes. If in this case it is countably infinite, you can still summing over these infinite series. If this omega is uncountably infinite, you cannot define the summation in a clear way. So that is when this equation breaks. So basically, in these cases, you can still apply the classic probability theory to address the probability problems. And the second special case is that in addition to this condition, so omega is finite and all outcomes are equally likely to happen. Okay, just like a flip a coin, fair coin. Now, in this case, if you consider an event that contains a bunch of outcomes, okay, then the probability of this event is simply because every outcome is equally likely to happen. So we just count the number of events, number of outcomes in this event over the number of all the possible outcomes. So let me just write it. Over the cardinality of omega. Right, the number of all possible outcomes in the omega set. So this is our classic way to calculate the probabilities when every outcome is equally likely to happen. For example, right, we have this very classic example. So flip a coin for 2 times. Consider 2 flips of a fair coin. So all the possible outcomes is, well, every experiments have 2 flips. So we are considering a combination of, well, every flip has 2 possibilities. So 2 flips have in total 4 possibilities. So we may get 2 heads, we may get head and tail, we may get tail and head, and tail and tail. So these are all the possible outcomes. And because it's a fair coin, so all these outcomes, they are equally likely to happen. Fair coin. So we can calculate the probability of at least one head is observed in these 2 flips of coin. We'll just calculate how many outcomes belongs to this event. Well, this is 1. We at least have 1 each. Here we have 2. This is another one. Here's another one. So we have in total 3 feasible outcomes. And then the total number of possible outcomes is 4. So the probability is 3/4. Okay, so this is a example where we are looking at every single outcome has equal probability to happen. And then we are looking at this omega set is either finite or countably infinite. So these are the 2 special cases where the classic probability theory actually meets the modern probability theory. Okay, and now let's talk about some advanced properties of the modern probability theory. So we just introduced the probability law.
we go back. So these are these 3 points. These are the axioms, 3 axioms of the probability law in the modern probability theory. Right? And these 3 axioms can imply many important properties that we are going to use. So consider let's consider a bunch of events that we picked from the sigma algebra that we have. Okay. So suppose you have you consider a random experiment. Now you have that big omega set. From that big omega set, you will consider some sigma algebra of events. Okay. And then let's consider some arbitrary events that we picked from that sigma algebra. Now this event, based on the axioms of probability law, we can have several useful properties. The first property is that if event A belongs to event B, so again, when we talk about events, okay, always remind ourselves that events are subsets of the big omega set. So basically, they are set. So then, because they are sets, so we can talk about inclusion and the intersection. So if the event A, which is a subset of omega, this could be omega. If event A is included in event B, now what can we say about their probabilities? So intuitively, event A is a smaller event. Now, intuitively, what can we say about their probabilities? Smaller, right? It has to be smaller because otherwise it's counterintuitive. Right? If B is a bigger event, then it is more likely to happen. But how do we justify, how do we show this from the probability, the axioms of the probability law? Well, this is, you probably will do this in the homework. So I will show this one. Basically, from this figure, you can see that since B is a bigger event, so B can be written as A plus the residual part, right? And these 2 parts, they are mutually exclusive. And since that's how we can leverage the probability law, the axioms of the probability law to prove this. So we start from probability of B. Because A is included in B, so I can write B as A union B minus A. Okay, so think about this. B minus A denotes this shadow part. It's the B, event B excluding event A. Okay, so it's A union with this shadow part. And apparently these 2 are mutually exclusive. Right, because this part has already excluded A. So therefore they have no intersection with each other. They are mutually exclusive. Now we have a union of 2 mutually exclusive events. So by the probability law, we can decompose them. And now we have this probability of A. Okay. plus some residual part. And we know that B subtracting A, this is an event, and by the probability axioms of probability law, this has to be positive. This has to be non-negative. Therefore, this is greater than equal to PA. Okay. You can see every step, in every step, we are leveraging one of the axioms of probability law to justify the proof. So in your homework, you should also follow similar strategy. Okay, always following the axioms and try to argue some the desired inequalities of proof strategies. But this is intuitive, right? If you have bigger event, it has to be more likely to happen. The second is also very intuitive. The complement event equals to 1 minus probability of A. Well, A complement is simply the biggest event omega subtracting A. Right. And this is intuitive because we know P omega is 1. So if you have A here, then the rest of the events, which is A complement, the complementary event must have probability 1 minus the probability of A. But how do we prove this using the probability axioms? So what is the key structure here regarding A and A complement? Yeah, they are disjoint, right? Mutually exclusive. So omega is actually A union with complement, and also they are mutually exclusive. Mutually exclusive. Now by this, we can start to write 1 equals to P omega, which is by the probability axiom. And now P omega is A union A complement. And these two are mutually exclusive, so we can decompose them. Right. Again, this is by the third axiom of probability law. And then you can conclude that this one equals to 1 minus probability of A. This also matches our intuition, right? So from these two examples, you can already see that probably the most frequently used trick regarding the probability axiom is to always considering constructing or somehow relating to mutually exclusive events. So it's all about this structure. Now the third one is a union bound. Which says that probability of this union events, let me write. For any sequence of events belongs to the sigma field, we have the probability of this union event is less than equal to the sum of the probability of individual events. So here I should note that here we do not require AI to be mutually exclusive. Right? Because if they are mutually exclusive by the third axiom of probability law, this should be an equality instead of inequality. Okay. So this property says that for any considering arbitrary bunch of events, their union event is always bigger than the probability of their union events is always bigger than the sum of the individual events. For example, we draw a figure. This could be A1. It's always less than equal to, sorry, smaller than the sum of their individual events, not bigger. Okay, so this could be the AIs. So if you consider the intuition is that since they are not mutually exclusive, meaning that they may have some overlapping. Now, when you union these events, the union event, the area of this union event is smaller than the sum of the areas of each individual events because of the overlapping part, right? That's the intuition, but we need to prove this. Based on the probability three axioms. Three axioms of the probability law. And this is part of your homework assignment. So I think here I will not go over that, but I give you a hint. It's exactly the same strategy as what we have done here and here. So try to, if you think about it, on both sides of the equation. Okay, on the left-hand side, you have this union event. On the right-hand side, you have this, all the events are separated. So you must think of a way to write this union event into a bunch of mutually exclusive events. For example, we can start from two. We can start from two events. That will give us a clear picture. So suppose we have two events. And they have a possibly overlapping part. So this union event can be written as it's A1. If you look at the right-hand side, we need to decompose it in a way so that we have all the individual events in the decomposition, right? You can decompose it as A1 so it's A1, let me see. I want to show that so I want to create a bunch of mutually exclusive events. Okay, how about this? Let's A1 union A2 subtracting A1 intercept A2. So A1 is here, right? This circle is A1 and the union this part. Well, this part is A2 subtracting their intersection, right? And these two are mutually exclusive. Therefore, you can say P A1 union A2 equals to, now these two are mutually exclusive, so equals to PA1 plus PA2 subtracting their union. Right. And then you have to argue that why this is less than equal to PA1 plus PA2. So think about that. Think about that. And once you have that, this only works for two events, right? You need to prove this for arbitrary number of union of events. Okay. I think once you get this idea from the two events, you can. The idea is straightforwardly generalizes to an arbitrary number of events. Yeah.
Second part is just less than probably 82.
Yeah, yes, exactly. So the second part is A2. Yeah, A2 subtracting something, right? So this is a smaller event compared to A2. So you can apply, then you can apply this property to justify finish the proof. Yeah. And the last one, this is actually very helpful for proving the previous one. So we have this inclusion exclusion formula. So for any finite number of events, we have, or you can call them sets, any finite number of sets. This union, the probability of this union event can be decomposed as follows. So I first simply summing up all the probability mass of individual events. But then because every two events, they may have possible overlapping. So I need to subtract those overlapping parts. Right? So that's why we have this one. And then, so this formula is very complicated, but you can understand it intuitively. Right. Now, when you subtract the overlapping parts between any two events, you are actually subtracting the union part of three events by 2 times. So you need to add this part back to the entire summation. So and when you do this, you are actually so this goes on and on. So when you're adding up the intersection part of every three possible events, you are adding the intersection part for every four possible events by 2 times. So right after this, you need to subtract the intersection part for every 2 events again, and then you have to keep doing that for 5 events, 6 events, and finally to the intersection of all the events. So, but this can be clearly seen from some special cases. So if we consider only 2 events, then we have this very simple formula. But this is formula that we are we are familiar with, and the proof. Well, the proof is very. So we have 2 sets, A1, A2, and let's call this part B1, this part B2, and this part B3. So apparently, we can start from the left-hand side. A1 union A2 is apparently it is B1 union B2 union B3. And these 3 parts, B1, B2, B3, they are disjoint. They are mutually exclusive. So I can write it as B1 plus right. I can decompose it. So it's probability of B1 plus B3 plus B2. And I just artificially add B3 here and subtract the same term. Okay, I didn't change anything, just artificially add these 2 terms here. And then these 2, P1 plus B1 plus B3. Okay, I think I made a mistake here. This should be B2, B3, 2. Yeah. Okay, it's B1, B2, B3, right? And then add B2 minus B2. So it's exactly the same. Now, and these 2, now B1 plus B2 is exactly A1 because they are disjoint. Right? And B2 plus B3 is exactly A2. And minus B2. B2 is exactly A1 intersects A2. Okay. Again, we are always utilizing the mutually exclusive structure of sets. And on the lecture notes, we have a formula for three number of. You can check it on the lecture notes. I will not write it here. There's another formula for this one. Okay. So to summarize, the only way we can we handle these union events is to decompose them into certain think of a strategy to decompose them into a bunch of mutually exclusive events, and then you can apply the probability axioms to justify your proof. Okay, so let's consider one example, practical example that we utilize in this mutually exclusive structure to calculate the probabilities. It's a very interesting problem called matching heads problem. So it's like we have n people, and everyone has a hat. Okay, so you can think about we have people 1, 2, 3, and n, and then we have hat h1, h2, h3, and hn, right? So every people has his or her own hat. Now what we do is that we collect all these hats from all the peoples, mix them together, randomly shuffling, and then return these hats to all the people randomly. Everybody grab one hat randomly. Now the question is what is the probability that at least one of the people gets his original hat? Yeah. So you collect this, you shuffle these hats, and assign them back to these people. Now, what is the probability that at least one of these people can get their own hat? Their original hat. Their own hat, let's say. So this is an event, right? So we can think about this problem starting from the basic structure of the probability space. So first of all, so what is the outcome space of this experiment? Right? You collect n hats, randomly shuffle them, send them back to everybody. What are all the possible outcomes? It should be all the possible perturbations of all these n hats, right? So in total, we have, so this should be the set of all perturbations. Perturbation means that you have n hats, and you randomly reorder their position. Every different perturbation is one possible outcome. So in total, we have, if you according to the perturbation calculation, we have this many number of possible outcomes. Okay, so these are the set of all possible outcomes. And for every realization, every possible outcome in this omega, we know that the probability of omega equals to 1 over the number of total outcomes, because we are shuffling it randomly, uniformly. So every outcome has the same is equally likely to occur, right? So the probability of every perturbation, every random reshuffle is the same. But now the question is, okay, now the question is that how do we calculate the probability of this event? This event includes many possible outcomes. At least one people get their own hat. Now the question is, we may have 1 people get their own hat, 2 people get their own hat, 3 people, up to n people. And for each case, let's say if 3 people get their own hat, now another question is, who are those 3 people? You need to select from these n people. So it involves a lot of calculations if we do it in a straightforward way. So a better way to, let's call this event A, right, this entire thing. A better way is to try to decompose this event into a set of simpler disjoint events. And for those events, it might be easier to calculate. So we can define AI be the event that the ice hat just call it AI, HI. The ice hat HI finds its owner. Okay. This event means the ice hat HI is somehow returned to its original owner. Then if you think about that, the event A, which is at least 1 people gets their own hat, is simply union of this AI. Because think about this, union of AI means at least one of the AI, at least one of these events happen, right? Now, if any of these events happen, that means a certain hat is returned to the owner, and you have at least 1 people gets his or her own hat, right? So this is a way to decompose this big event A into a bunch of smaller events. And here, if you look at this AI, the fundamental question is, are they disjoint? Are they mutually exclusive? Each AI considers the ice hat finds its owner. It may happen that 2 different hats finds their owners, right? So they are not exclusive. They may have overlap. They may happen at the same time. So these AIs are not mutually exclusive. Therefore, to calculate PA, you cannot apply the 3rd axiom of probability law. It is not the summation of all the AIs, all the probability of AIs. However, because this is a union event, we can leverage this exclusion formula, right, to decompose this union event. So we just calculate every single term in this event, and let's see if it is doable. So you realize that to calculate this terms, you need to calculate PAI for every AI. You need to calculate probability of every two intersection of these two events, and also the probability of the intersection of three events. Keep going on up to the intersection of every n events. But then when you do the calculation, you realize that these intersection events, they are relatively easy to calculate. So let's do it, quickly do it here. So PAI is the probability that the ice hat finds its owner. So it's simply, well, this event means that, okay, the ice hat finds its owner, but all the other, we don't really care about all the other people. So in this case, so how many possible outcomes falls into this event? It is n-1. It's like all the possible perturbations of the rest of n-1 people. So it's n-1 multiplied by n-2 up to 1 divided by all the possible outcomes. Right. So here we can utilize the classic probability theory to calculate the probability, because every single perturbation is equally likely to happen. So we just calculate how many possible, what are the total number of desired outcomes divided by the total number of outcomes. So here we are looking at the ice person gets his own hat. Now, the rest of the people can have random perturbations. So here we have this many number of possible outcomes. So this is PAI. And then for PAI intersection AJ, for any intersection of two events, it's the same thing. So now two people have their hats back. So the rest of people can be randomly reshuffled. So this has, for the rest of n-2 people, they do a random reshuffle. So we have this many perturbations over this many total perturbations. So we get this. Okay. And then you keep doing this. Turns out all these calculations are very simple. Okay. Until for the last one, well, you consider all the possible intersections. And in this case, this means that every person has their hats back. So this only happens with one single realization. Right? So it's 1 over this. So you have all this intersection, all this probability of all these intersection events. So you can plug them into that inclusion exclusion formula. So what you get is if you go back to this formula, like this is n choosing 1. This summation over all the possible ij, where I smaller than j, this means in total we have n choosing 2 number of elements. Here we have n choose 3 elements, and in the end we have n choose n elements. So the coefficients are defined by the combinatorics. So these are the number of terms for the first summation, and for each one we have this many probabilities. So just plug them in, and for the second term we do minus. So we have n choosing 2, and the probability is this one. Okay. For the third term we do addition. n choose 3, the probability is n minus 3 over this one. And you keep going until you have the last one is n choosing n. Okay, so you can read for the rest of the calculations, you can follow the lecture notes, but in the end, you get this one. This is a summation of finite theories. But we have this, just write it here. But as n goes to infinity, we can see the more and more number of people, this summation goes to 1 minus e negative 1. So it's about 63.2%. Yeah, so if you consider sufficiently many number of people randomly shuffling their heads and return them back, you have this many probabilities to have at least one people find its own head. Okay. So here again we are leveraging the this union event and leveraging the inclusion exclusion formula. So okay, I will stop here, and if you have questions, I will be in the same class Zoom between 1 and 3 p.m. this afternoon.